omega, phi, and the offset b, if it has any. So far, phi and b have been equal to 0. And now 12 is going to be a little bit different as I look at it over my shoulder here. Let's go down to 12. And again, we're trying to compare it to a sine wave over here, as you can see. Okay, let's see if we can find the amplitude. So it looks like it goes from minus 0.5 to plus 0.5. That's a distance of 1. The amplitude is half of that, so my A is 1/2. And we also know that it goes the same minus 0.5 to plus 0.5, so the offset B is 0. There is no B. Okay, now it's, let's take a look if we can, we get some shifting over here. This is a little bit harder to do to try and find it. But what you can do is if you kind of go through one complete cycle, you could say I start over here and I go through one complete cycle over here. So notice what I have. I'm trying to pick out an easy way so I can go straight down and read the coordinate along the theta axis. The easiest way of doing that is just two ways of doing it. I could either go from this peak to that peak, and this peak occurs at theta is negative 4 pi over 3. This peak occurs at theta is equal to 2 pi over 3. So that distance is 6 pi over 3, which is equal to, in this case, you can see just 2 pi. 6 pi, take 6 pi divided by 3, okay, because I get 4 pi and 2 pi is 6 pi over 3 gives me 2 pi. So my period is 2 pi. You could also look over here. The two values, minus pi over 3 and 5 pi over 3, the distance from here to here is also 6 pi over 3, which is 2 pi. Okay, so my period is 2 pi. Now the phase shift here, this is where we're going to do some estimating over here, because it looks like, this distance here is, from here to here is pi over 3. It looks like it's halfway between that, because this sine wave should be over here. Okay, so it looks like it's about half, and we'll estimate because it's where this peak occurs over here. So this peak over here, really, if you kind of move it, 6 pi over 3 would move. So we'll plug in those details as we get. So hopefully everyone's got a picture of that in their mind, and we can start calculating the various A, omegas, etc. So from looking at the picture, we determined that A has to be 1/2 because the amplitude is 0.5, and it looks close to, takes my sine wave went right through here, and that'd be +5. So then it's shifting down a little bit. So it's going to go in the positive direction. So it's going to be in this case, what do we want it to be? So we're trying to compare it to this. So this is what we want to compare it to. F of theta is equal to A, and it says use the sine function. So it's A sine omega theta, and it uses here minus phi. It's kind of a little bit different, plus B. Okay, so what do we have over here? So we know the period we just got was equal to 2 pi, and the period is equal to 2 pi over omega. So this tells me then that omega has to be 1. Now, what is my, if I'm going to use this as my model, I can take the negative of phi. So this over here, we want to figure out phi. It looks like the phase shift looked like for us it was pi over 6. Well, that's equal to, we'll worry about the sign in a minute, minus phi over omega. But omega, we already found that was just equal to, in this case, 1. So that means my phi over here looks like it's going to be essentially equal to just, pi over 6. So if I put the 1 over here, I get my phi is pi over 6, and we'll worry about the sign in a minute. It's symmetric. This distance and that distance is symmetric, so b is 0. There is no offset. It's going plus or minus 0.5 forever and ever. So let's put that in and see if it does give us what we would expect in our rendition using, in this case, Desmos. So let's start f of x is equal to, and we have 1/2, or I'll do it as 0.5 times the sine of, so omega is 1, so I just have x minus the pi, x, yep, what did I do, x minus pi over 6. And let's kind of change the scales down here. We'll go in increments of pi over 3. Let's go from minus 3 pi, oh, double negatives there, gotta be careful, to 3 pi. And that's my step go pi over 3. Let's go from minus 1 to 1. So taking a look at this graph here, so I can close this up over here. So again, you can see my peak is minus 4 pi over 3 to 2 pi over 3, just like the other one, or minus pi over 3 to 5 pi over 3. And there's my kind of the shifting down here was kind of went from there to there. It went to a total of pi over 6. So if I compare that to the other graph, same sort of thing, minus 4 pi over 3 to 2 pi over 3, right in the middle. So you can see I've demonstrated that I get the same sort of thing. So I can then rewrite what the function looks like now. So the actual function I'm dealing with is my f of theta is 1/2 sine, omega is just 1, so it's x minus pi over 6. That's what I'm looking for. It's a little bit harder because it's not, you just don't get those things algebraically. You have to kind of work for them. Okay, so let's take a look at number 13 now. Move all this. In fact, I don't even need that anymore. Clear it all out and make some space over here. So this is what you should be able to do. You're trying to pick out all the features of a trig function, either given it algebraically or graphically. If you can do that, then you understand everything there is. You can look at it from the graph and come back and get the parameters a, omega, phi, and b. Or you can look at the, the algebraic representation of it, and you can pick out a, omega, phi, and b. And that's all it is. Okay, so now number 13. Let's take a look at that one. And we again want to find a, omega, phi, and b. So I can plug them into this representation. It's saying use the cosine. So f of theta is the a cosine omega theta minus phi plus b. Okay, now let's look at the graph and see if we can pick some of these things out. Just like we've been doing all along, we'll continue on that pathway. So let's go to 13. Well, first thing we see, there is an offset. So, but let's first get the amplitude. So it goes from -3 to -1. So this distance from here to here is 2 units. So the amplitude is just 1. Okay. Now the other thing, you can see the offset. So this -2 should actually be along the theta axis over here. So my offset is down 2 units, -2. Now, if I shift this entire graph up 2 units, it's going to look exactly like the cosine, because remember, the cosine starts on the y-axis, and then it goes down. So it's a positive on the cosine, right? So A is 1 cosine. Now let's see about going from peak to peak. Well, this one peak occurs when theta is 0, and this peak occurs when theta is 2 pi over 3. So that's going to give me some information that I can use to find omega. Now, since it starts right at the origin, I know phi in this case is 0. There is no phase shift because it is exactly the cosine when I shift it up. If I got rid of B and made B 0, this would just shift up and it would just start over here at 2 and come down. Okay, so let's see if we can take that information and find the A, omega, phi, and B. So A, we saw that because it just goes from -3 to -1, total distance of 2, it's half of that, so A is 1. And the reason it's positive 1 is because cosines, remember, start up here. But this one is now shifted down because that's what we here. B is a phase shift is down 2. I mean, that's phase shift, but the offset is down 2. The phi over here is 0 because it's perfectly aligned over here, so that's 0. The only thing we have to figure out is the omega. So the period, which is 2 pi over 3, was equal to 2 pi over omega. So we can see that very simply, omega then is 3. So now I can write my, if I want to, my function algebraically. So my f of theta, A is 1, cosine 3 theta, phi is 0, but then I have -2. Let's just do that. Let's just see and give ourselves, comfort and confidence that that is indeed what it looks like. So take our cosine theta, or x I'm going to use, or 3x, excuse me, 3x, and then -2. Cosine 3x -2. You kind of see what's happening over here. Let's see if we can move it a little bit better so we can see this a little bit more. The x I'm going to go from minus pi to, excuse me, minus pi up to, say, pi. And that's kind of good enough there. So you go from 0 to 2 pi over 3. That's what we saw over here. -3 to -1. And it's not shifting around. So that compares exactly to this, what I have over here. Again, take a look at the two of them together and you can kind of see that. Hopefully you can see that. Gives me the same thing. So this is my functional form of that graph. It's always harder. This is always harder, but it tests whether or not you really understand fully what all those parameters mean and do in this functional form of that cosine function here. Any other questions? Any other questions on some of these things? Anything else that you're not sure of? Essentially, we looked at all of the graphs and saw all of those. We looked at a lot of these other functions over there, but these tend to be a little bit more complicated or challenging, but hopefully you can see. When you want to find omega, find the, peak to peak, valley to valley distance, and that's your period, and your period is always 2 pi over omega, and then you can solve for omega. When you want to find the offset, you can see if it's shifted up or down, you're going to have an offset. If it's kind of like, equally going between above and beneath the x or theta axis, the offset is 0. Now, if you choose a sine or a cosine and it doesn't, for the sine, go through the origin, and for the cosine, its peak is not on the y-axis, then it has a phase shift. So what you can do is you can measure the phase shift, and then for the phi, you can use that phi as minus, phase shift is minus phi over omega, so you can kind of time for tomorrow for this as well, but we don't need it, I'm thinking, unless you look at it again and there's something you're not sure. So tomorrow is our shorter class and stuff like that. And then we're going to be looking at exponentials and logs. So it'll give us some more time to be able to do those as well. But any questions now? This is all the analysis that you need to kind of be able to perform when you get to the calculus for trig functions. This will give you a good head start in understanding the features you want to pull out of these things. Now, trig functions are very useful in modeling things that are cyclical, especially like in alternating currents, a very popular thing to do. Also in acoustics, modeling of sound vibration and waves using this. And change the frequency, you get different pitches and sounds. If it's a vibrating speaker, you get to hear that, or instruments. And then there's also some harmonics in instruments. So you can study everything about trig functions and really understand the subtleties of music and the subtleties of the specific sinusoidal signatures of the different instruments. Even though they play the same note, they sound differently because they have different harmonics that are actually going based upon an instrument. And that's a whole thing about the mathematics of music. And that's what synthesizers do. They kind of, emulate what a horn will sound at versus a piano with the same thing. They have studied and they know how to create the sine waves and put the harmonics in them and kind of make it, give you the sound that you're hearing and make it sound very similar to instruments. And that's the mathematics that enable that. Otherwise, you would never have those synthesizers to be able to do that. But any other question? Anything else? So we're coming down to the end here. We have just a little bit more to go. Let's take a look at the following thing here. So if I go and look at our, if we have it over here, I have one wheel. Let's see if I can, I have to go back and see if the courses work or not. In fact, I might even have it up here. Here we go, here we go. Here's our schedule, so I can just take it to that. So we're coming down over here. So here's the 21st. So we did all of 11.5. I had some reserved time for that. So tomorrow, what we'll do